Hi there, this is a video for section 1.4 on how to write an exponential function. I'm also going to be describing how we know what an exponential function is. In other words, the definition of an exponential function. All right, well, there's many ways that people write an exponential function. If you watch some of my previous videos, I gave a couple of ways that people write equations of lines, y equals mx plus b, and the y minus y1 equals mx minus x1, the version they used more typically in calculus. There are even other ways of writing equations of lines, and this same situation happens with many different types of functions where we can write them in different ways. So the two that we're going to be focusing on in calculus are y equals a times b to the x. That's a times. And then also we have y equals a times e to the rx. And just to be clear, because sometimes it's been a while for folks, e is not a mystical symbol in mathematics. E represents a constant where E is 2.7182. It's one of these numbers, irrational numbers that go on and on forever. The analogy would be like pi. Pi is a number that goes on and on forever. You're more familiar with it. It has to do with circles. And people usually memorize it as about 3.14. Well, you should memorize, I'm just writing this more clearly, 2.7182 dot dot dot. You should definitely memorize what E is. It's just a number, just like pi is a little bit bigger than 3. E is an irrational number, a little bit smaller than 3. So just have an idea of what that is. It's not something to solve for. It is a known number, just to be clear. All right, so what is an exponential function? It's not just an equation. We don't necessarily have everything in equation form, so we do need to understand the definition of an exponential function. And to help you understand the definition of an exponential function, I'll remind you about the definition of a linear function. A linear function talks about the fact that if we're moving up x's by the same amount per one each time, that's supposed to be an arrow, then y would add the same amount each time. The amount we're adding each time would be the slope. In this particular example, in the first couple of points from 2 to 4, y added by 2. In the second couple of points from 4 to 8, y added by 4. And the last couple of points, y added by 8. So this is not linear, right? Because there's no constant rate of change. But for those sharp-eyed viewers and those who like to try to recognize patterns, you may notice that the pattern is not additive for this problem. We're not adding the same amount from one y to the next, but we are multiplying by the same amount. If I take the first y value and multiply by 2, I get the second y value. And I take the second y value, which is 4, and multiply by 2, I get 8, which is the third y value. And likewise, each time I multiply by 2, I get the next y value. This only is a recognizable pattern. If x increases by 1 each time, if x jumps around, you're going to have to do some more calculations to see if the per 1x is the same multiplication by y. So what is an exponential function? It has y changes or multiplies by the same amount for each 1x. Again, if you skip around the x's, you may not see that y multiplies by the same amount, but I made this example a little bit easier for us to see. If x increases by 1 every single time, then y multiplies by the same amount for each of those 1x values. This multiplying by the same amount is not called slope because slope is how much it adds. So multiplies by the same amount, the amount is called the growth factor. I wish it has a one-word name, but it does not. So blame math people for calling it growth factor. And so, in fact, some mathematicians call it growth decay factor, which in my mind is even worse. It's even longer. The reason why they say growth decay is linear equations can go up, linear equations could go down. So you have increasing or decreasing. Exponentials can go up, exponentials can go down. So again, you could have growth or decay, increasing or decreasing. So that's the idea of what an exponential function is. It's a situation in which y multiplies by the same amount for each increase of 1 in the x values. All right, so let me show you a very powerful tool about how to find an equation given a model and some data. This particular strategy works for any model and any data points. So I am showing you here for the exponential, but we're also going to be able to use this for any type of equation that we want to find, sine equation, log equation, whatever we want to do. So good method to learn. Here's some data points. I tend to write my data points in a table because I see things better vertically than linearly. So excuse me for a moment while I write these out in a table. And we're going to be using the model y equals abx. You can also use y equals aerx if you like. As I mentioned before, they are just two different ways of getting the same answer. They're equivalent. They just look a little bit different the way that you use them. In fact, I'm going to be finding it using the y equals a times b to the x model, and then I'll just convert it over to the aerx model. I'm not going to redo the problem. I'll just do a conversion and show you that conversion. All right, so how do we find the equation y equals a times b to the x if we know some data points 3, 6, and 554. The key idea here is you just substitute. We know that this is an XY pair. We know that 3, 6 literally means when X is 6, we have to have a Y value, when X is 3, we have to have a Y value of 6. So I just put them into my equation, making sure to put the correct number in the right place. A and B, I do not know, but X and Y, I do know. And we're going to do that with both set of points. So each point you're given is information you can use. So I'm going to use the 54 for the Y and the 5 for the X. So there's two equations we have. These two equations have the letters A and B in them. We don't know what A and B are, but when you have two equations that come from different sources of information, and they have two letters that overlap, we can solve. Anytime you have two equations with two unknowns and they're actually independent equations, you can solve for A and B. This is just the basic algebra skill that you may have seen before, hopefully, but we'll need to practice it if you don't remember how to do that. There are different methods for doing this. The most straightforward method that I'm going to show you is just substitution. Substitution will always work for any of these problems. You don't need to have any tricks or special techniques for special types of equations. You just solve for one of the letters and substitute it into the other equation. So what do I mean by that? Well, in this equation right here, I have the letters A and B. Personally, for me, it's easier to solve for A. I can get A by itself in one step just by dividing by B to the third power. B to the third divided by B to the third is 1. And anything times 1 is the same. So we just get A here. And on the left-hand side, we do get kind of a mess. 6 over B cubed, but that's okay. It's algebra. Algebra is messy. So we're going to take this expression for A. We solve for one of the letters. It doesn't matter. You could have solved for B. It just takes more steps. And we're going to substitute that into the other equation. Now, of course, we're putting in for A because it tells us what A is. Okay, so let's actually put that equation for A into our other piece of information. So we still have the 54. We now know what A is equal to. A is equal to 6 over B cubed. And don't forget that we still have a times B to the 5th at the end. All right, I'm just going to get rid of that fraction, or at least a fraction times a whole number, by combining it into a single fraction. So 6 times B to the 5th is just 6B to the 5th. And I have B cubed. We have a B to the 5th on the top and a B cubed on the bottom. We have 5 B's multiplied on the top, 3 B's multiplied on the bottom. I'm going to be able to divide 3 of the B's from the top and the bottom, all equaling 1. Or, as some of you may remember, you could just subtract the exponents when you're dividing powers with the same base. So I'm going to subtract 5 minus 3 and get B to the 2. Or after dividing out 3 of the B's, I end up with B squared left over. So once again, substitute, simplify, and then you may actually see what to do at this point. We're just trying to solve for B. So I'm going to divide by 6. I'm running out of room, so I'll just continue up here. 54 divided by 6, I believe, is 9. 6 divided by 6 is 1. I know that one, so I'm left with B squared. I will need to square both sides to get B by itself. Square root of 9 is 3. The square root of B squared, if you remember from my previous video, is the absolute value of B, not B, is the absolute value of B. Some people write this as plus or minus B instead of using the absolute value. In fact, some people write the plus or minus on the other side instead of writing it next to the B. All those are fine. Just don't assume that it's B. It's 3 is the absolute value of B, or one of those equivalent versions up below. So we have 2 different values of B. In some cases, both values of B would be correct answers. But sometimes only one of them is a correct answer. And in rare situations, neither of them is a correct answer. It is possible to have a solution algebraically that does not check. So we do need to check to make sure if one or both of these is a proper solution. So it turns out B equals 3 does check. But B equals negative 3 doesn't check. And the reason why is you can't have B is less than 0. So one of the characteristics of exponential equations is that you can't have a negative B value. It becomes a non-continuous function and not something that we can even graph or even deal with. For example, if B was a negative number like negative 3 and you raised it to the 1/2 exponent, that would be equivalent to the square root of negative 3, which is not an actual answer. It's a complex number or imaginary number. It's not graphable on a normal XY plane, and we can't use it to solve our normal equations. So we have to get rid of this one right here. And B equals 3 is the correct answer. And now we can actually find the result. Since I know B is 3, I can put this into any equation I want and solve for A. I'm going to put it into this first equation just because it has A by itself already. So I have A is equal to 6 over B cubed, but I know what B is. B is 3. So I get A is equal to 6 over 3 cubed, which gives me A is 6 over 27. Please simplify your answers. That means if I divide top and bottom by 3, I get 2 over 9. So I know the value of B. It's a positive 3. I know the value of A. It's 2 over 9. So now we know how to write A times B to the X. So our model is Y equals A times B to the X. We just found out that the value of A is 2 over 9. and the value of b is 3. And so that, my friends, is our exponential equation in y equals a times b to the x format. Now, I did mention that we could also convert this into y equals ae to the rx. So let me show you the conversion. So the other model that typically used looks like that, where e is that number 2.718. If I just quickly compare this to my other model, you may see that some of the letters overlap. For example, the y's are both by themselves on the left, which is very typical for equations, but the a's also line up perfectly, and the x's line up perfectly. Now, if these two equations were genuinely equal or equivalent, then the top and the bottom must match up. So everything's matched up so far except for this b and this e to the r. So those have to match up as well. Otherwise, the two equations wouldn't be equivalent. So we must have, or we need, b is equal to e to the r, right? If the b in our y equals abx is the same as e to the r, then the two will match up. Well, we know what b is because we actually just did it before. So it is 3. E is known because it's 2.718. And r is the thing we need to find. R is the unknown in this equation. So we have to solve 3 equals e to the r. This requires logarithms. Logarithms are the inverses of exponentials. It's how we solve exponential equations. So I take the log of both sides. So I'm going to take the log of the left-hand side and the log of the right-hand side. I'm using ln, which is log base e. Because I'm using log base e, the ln and the e will undo each other. I have a function with a base e, a log function with base e, and I have an exponential function with base e. That's the same base, so they'll undo each other. So that leaves ln of 3 is equal to r, and that's the number that goes into that equation right there. All right, so finally, I can write my answer. Again, the model is y equals a times e to the rx. I know a because a was from before. It's the same a value, right? Remember, a was 2 knights, so a is still 2 knights. E is just the 2.7 number. I leave it as e. R, we just figured out was ln 3. And then, of course, we have our x. I'm going to write times x just so it's clear that it's a multiplication up there. So this is my converted version of the exponential that matches the data. All right, well, if you have not already done so, this is a good time to try the next problem yourself. We have example C right here. Find an exponential model that passes through the points 2, 8 and 5, 1. So if you're willing, please give that a try. Pause the video and then come back when you have gotten sufficiently far. Or if you get stuck, that's okay too. At least you know how far you got. And then when you get stuck, you can see how to get unstuck from my solution. All right, so welcome back. If you did give that a try, thank you very much. I'm going to write these vertically just for my own benefit. I'm going to put them into the model of my choice. I'm going to choose y equals abx just because it's easier for me to solve for a and b. But if you chose y equals aerx, that's equally viable. It just takes another step or two, in my opinion. So unless the directions specify which model to use, you're free to use whichever one you prefer. I'm going to stick in the x and y values. like that. So I stuck in the 2 and the 8, making sure to get the x and the x and the y for the y, and likewise for the 5 and the 1. Then I'm just going to solve for a in one of the equations. It doesn't matter which equation you solve for. I'll just do one on the left just to be consistent, but honestly, I think it's actually easier to solve for a and the one on the right. But I just divide by b squared. It's about the same, actually. So I solve for a, and then I take this and I substitute it into the other equation. It's called the principle of substitution. All right, so my a is 8 over b squared, and I have a b to the 5th. I do need to simplify these things. I'll write them as one fraction just to help people visualize what's going on here. I have b to the 5th on top. I have 5 b's on the top, 2 b's on the bottom. That's going to leave me 3 b's left over, or you can subtract those two powers since they have the same base. Oops. I get 1 on the bottom, which I don't have to write. All right, and then I need to solve for b. I'm going to divide by 8. And then I'm going to cube root. Maybe I'll show you the cube root. So up here. So I'm going to do the cube root on both sides. Now, we don't really do cube roots too much in higher level mathematics. If you remember from your previous algebra work, you may or may not, we use fractional exponents instead of cube roots. So this would be 1/8 to the 1/3 exponent. And then we would have b to the 3rd to the 1/3 exponent as well. This is supposed to say 1/3. And this will say 1/3. It doesn't matter which way you do it. I'm just saying in calculus, we use fractional exponents because you could do math with numbers. You can't do math with roots. For example, I can multiply this 3 times the 1/3 because of the exponent properties. And 3 times 1/3 is 1. So this becomes b to the 1. And here I can't really multiply anything, but I can do 1/3 to 1/8 to the 1/3 power, which is the cube root of 1/8, which is 1/2. And b to the 1st power is just b. So I know the value of b. b is 1/2. And then, of course, I can just put that into the equation. Any equation will work. I can put it into any of these equations. This equation will work. This equation will work. Any equation you can plug the b into and solve for a. I'll just use this one over here since it's already solved for a. b is 1/2. Let's put it in green to emphasize. And that is being squared, right? It's 8 over b squared, so I have to do a square here. So now I'm going to simplify for a. 1/2 squared is 1/2 times 1/2, which is 1/4. Dividing by a fraction, dividing by 1/4 is the same as multiplying by the reciprocal, or you can multiply top and bottom by 4 to simplify that. And so we get an a value of 32. Now we know my a and my b. Remember my model was a times b to the x. I do know the value of a, that's 32. And I know the value of b, that's 1/2. And that is the answer to this other example on finding an exponential model that fits some given data. All right, so that was my video on what an exponential function is and how to find the equation of an exponential model given some data points. Feel free to reach out if you have any questions or want to see me convert this into y equals AERX, or if you have any other questions, I'd be happy to help you. All right, thanks for watching.